Welcome to Heart of Mathematics. Today's topic is on complex fractals. So let's define a couple of terms first. First, we'll define what an imaginary number is. So an imaginary number is usually represented with the symbol I, where I is given to be equal to the square root of -1. So if you take I and you square it, you're taking the square root of -1 squared, and you multiply that and you get I squared is equal to -1. So this goes against many of your intuitions where you can't have a square root underneath the negative sign. And that's because we say a real number doesn't exist if you have the square root underneath a negative sign, but in this case, an imaginary number does. So we define a complex number as where you take a real portion, A, plus an imaginary portion, BI, and you form a complex number, usually represented with Z. So Z is a complex number where Z is built of some real parts, A, and some imaginary parts, B. And we define the modulus, the size of Z, to be the length of the vector that has that distance, A plus BI. So the absolute value of Z is what we call the modulus of Z. This is like absolute value in real numbers, but now we account for the imaginary component here. So when we're looking at fractals, there's a couple of different fractals that come into play with complex numbers. And the first is the Mandelbrot set. So the Mandelbrot set was discovered on accident, actually, in the early 80s, I believe. And so this is a representation of one of the first images of the Mandelbrot sets before pixelization really got itself together. So the idea of a Mandelbrot set is it's produced by an iterative mapping. So with fractals, we see this idea of this self-similarity, this replicative sort of behavior, this iteration. And this is what Mandelbrot sets have, is this iterative mapping where you feed in, you take an input, Zn, and you feed that into a function, you do something to the input, and then you get out the next step. And the iterative mapping, the Mandelbrot set, says take my next step is given by my current step squared plus some complex constant. And I choose to start at the origin. And if this stays within 2 units of the origin, if my modulus of my Zn is less than 2, less than or equal to 2, then I consider it that it's in my Mandelbrot set. So let's look at a couple of examples here. So if I look at the value of C equals 1, if I'm starting at 0, so Z1, so here's my Zn, my Z0 equals 1. My starting point is always Z sub 0 equals 0, so my initial point is 0. So I take 0 squared plus my C value, C equals 1, so I get 1. This feeds back into my new value here. So this is the iterative mapping. This 1 feeds back in to the new location. This is what makes it the iterative mapping. My C equals 1, so this is 2. My Z3 is equal to 2 squared plus 1. Again, the 2 feeds back into my iterative mapping. So I get 5, and I can see that this is quickly zooming off to infinity. So this is unbounded, so it can't be in my Mandelbrot set. So it's not in the set. But if I look at Z equals -1, again, starting at Z sub 0 equals 0, and so I have Z1 equals 0 squared minus 1 equals -1. Z2 equals -1 squared minus 1. Keeping that C value the same, I get 1 minus 1 equals 0. Z3 equals 0 squared minus 1 equals -1. So I see this back and forth of -1, 0, -1, 0. So this stays bounded. So if it stays bounded, it's in my set. And so if it stays bounded, it's in my set, and we see that this point, -1 at C equals -1 is in my set. But my C value of equals 1 is not in my set. And here we represent values that are in the set with a dark bound inside the dark image here. So one interesting thing about Mandelbrot sets is that sometimes it's nice to visualize these with different colors. And so oftentimes, to see the nice images that you see floating around the internet, the coloring is based on how long it takes for a point to escape. So inside this purple color here, again, here is your C equals -1. Your origin is somewhere in right about here. Here is your origin. So inside the purple area, those points never escape. Those points are always solid and they stay within the set forever. Now, outside the purple, as the colors change, that indicates that some of the points have escaped faster or slower. So we see that there's this kind of boundary here, this little edge right about here. This is our circle of radius 2. And this is our boundary point. So anything outside of the radius 2 is already gone because that's our boundary edge. And if you look carefully with the colors, and we'll do an example of this in a moment, we can see that the color gradient changes as we kind of get closer and closer to the circle. You see that you've got some colors here, here, and here. So we see the color gradient is changing as we get closer in to this, to the Mandelbrot set. So let me erase those particular lines. And so the brighter the color is, the longer it has taken for those points to escape. And so this is a way of visually representing what's going on with the curve or with the set. So darker colors in this particular coloring indicate that the points have escaped faster, and the very brilliant yellow colors indicates that the points have stayed. It's taken a long time for those points to escape from the Mandelbrot set. So there's some other complex fractals that we'll talk about before we do some simulations. There's the Julia sets, which look a lot like the Mandelbrot sets in the same sort of function. One representation of the Julia set is z squared plus c, where you get to choose your value of c. And then instead of looking at all the c's that don't escape, you're looking for all the values of z's that don't escape under the mapping. And these help build Mandelbrot sets. And so these are two examples of Julia sets with different values of c. And we can see they've got some really cool, beautiful patterns here. You can almost see some seashells. You can almost see seahorses. Those are some different cloud shapes. Those are some different representations that we see. Another interesting fractal that we see is called the burning ship fractal. And this is where you take the Mandelbrot set, and this here is Zn in the Mandelbrot set. But what we've done is we've taken the Mandelbrot set and we've taken the absolute value of the pieces and then taken those components and then squared them to look to see what is going on, not just with the values with positive, negative, but looking at the absolute value of the components first. And we get what we call the burning ship fractal. And this fractal was discovered in the 90s. So fractals aren't necessarily old and bold. They've been around for a long period of time. So we're going to switch to some MATLAB, and I'll show you some different examples of fractals. And we can step through a couple of iterations here. Okay, so let's take a look at this MATLAB code. So this MATLAB code is set up to generate the Mandelbrot set. So if I generate a Mandelbrot set with 800 iterations or 800 steps and 50 iterations, I can get something that looks like this. So this has, again, at -1 here, we see the bulb. At 0 here, we see the bulb. So the dark color indicates that we haven't escaped at all. And as the reds get deeper and deeper into the red, that's the escape velocity. So the redder the red, the more deep the red is, the faster it's escaped. So this edge here, this is a circle of radius 2. So anything outside of the circle, they've already escaped. And so we can change the number of iterations. So if I look at just 2 iterations, or I can see that things have stayed in the circle because I've only taken 2 steps out. If I've looked at 20 iterations, I can see this shape. And let's compare 20 iterations to 200 iterations. Let's see if we can see a difference here. 200 iterations, so let's pull up figure 4 and figure 3. So figure 4 looks a lot dimmer than figure 3. So figure 3 looks like we see a lot more detail in the escape because we've only done 20 iterations. So there's only 20 little levels of color here. So compared to 200 levels of color here. So some of this has to do with the way that we're rendering the different colors. We're taking 200 different colors and trying to render it versus 20 different colors and trying to render it. We can pull up our original figure here. This was 50 colors and compare it to the 20 colors. So obviously with the 20 iterations, we don't get the crispness of the detail as we can see in the bulb here up in the top. You can see in the bulb in the bottom here. Let's see if we can zoom in a little bit. Maybe not. So if we zoom in there and zoom in there, you see that there's a distinct difference in the crispness of those two details. But the idea with the Mandelbrot set is if we close all these figures out, we can change the size and the number of iterations, and we can get different sort of numbers of pixels. If I do 450, I can see that my pixel size has changed. I can look at different sorts of shapes here. And so this is kind of an interesting way to play with the Mandelbrot sets. We also have, in this program that I have set up, I have for the Julia function, for the Julia sets, I have, oops, okay, we have this beautiful graph here. So this is an idea of a Julia set. I give it a starting value and this generates the Julia set. But we can do the Julia set with any particular value. So this is another different Julia set that we have. Obviously it doesn't look as cool, but on the other hand, this almost looks like a brain. So instead of putting in a complex number, I just put in a real valued number. But I can put a real valued number plus a complex number, and I can get something different. And so that's the really cool thing about this program, is that as I change that particular value, I can play around with the values and I can start to see how these Julia sets change. So changing from 0.5 to 0.58, right? So this is the image before, and this is the image now. I can see how my set has moved a little bit. And so if I change this down to just I can see, I'm starting to see that there's, the lower my value down here, 0.1, I can get some different behaviors. And so these are just really different, interesting sets. And there's a lot that you can do with Julia sets. And a lot of different visualizations to get these really cool, pretty colors. And again, the colorization happens to do with the escape velocity, how long it took for it to escape. So the darker color indicates that it took a longer time to escape. In this case, darker blue means it took a longer time to escape. And you see the gradients through here. So I'm happy to share with you the code for this and happy to talk you through it if you have any questions. As always, let me know.